I know everybody knows me very well.
Yes,
So,
sir. No, I was starting the recording. That's why, sir.
okay.
Okay.
But we can go ahead also. My introduction is not required. Introduction of speaker is more important.
Okay, so no problem. So, sir, I'll hand over the session to you. You can read the biodata of the speaker and we'll start the session without wasting much time, sir. Thank you for your presence, sir.
Okay, thank you. So, good evening all. Ramesh Kulkarni here. I'm going to read short biodata of the speaker, Mr. Tejas Belani. Tejas is currently associated with Messrs. Airport of India as Principal Geotechnical Engineering College, Vadodara University, Vadodara in 2000, exploring ground conditions, and he worked in various projects from oil and gas, infrastructure, railways, nuclear, ports to chemical industries. His current role includes engaging in site selection for mega projects across the globe, identifying geotechnical hazards and proposing mitigation plan, assessment of ground conditions, providing ground improvement solutions, earthwork design, use of existing foundation, geophysical investigation, planning, coordination, and monitoring of investigation works for the projects. He has published papers in international and national conferences. He is a member of Indian Geotechnical Society and American Society of Civil Engineering. He believes in sharing his experience and insights. He delivers expert lecture in various colleges and institutions and participates in panelists in various forums. So over to you, Tejas.
Thank you, sir. Thank you so much for your kind words and kind introduction. Having this wonderful opportunity to share my experience with geotechnical fraternity, I would like to thank also Dr. A.P. Singh, sir, who is the Honorary Secretary of IGS Delhi office, and our SC3 committee members who are running this series of webinars to help our fellow engineers to understand the criticality of the geotechnical engineering. I would also like to acknowledge and appreciate the efforts and support provided by Dr. Jay Kumar Shukla and Engineer Nazim to make this session happen today. Thank you all. I'll just share my screen. I think somebody is sharing screen. I believe I can share my screen, right?
Yes, sir.
If Sudhir Das is sharing screen, he should close his screen.
Are you able to share your screen?
Yes, let me know when you can see my screen.
Yes.
You can see, right?
Yes.
Okay. Fine. So when the word challenge crosses our mind, obviously we start seeking ways to mitigate as a part or as a whole, right? And eventually the best way is to understand it by assessing the challenges, the condition or state of problem, and then selecting best possible solution to those challenges in a given time frame. So today I'm going to present three case studies. Just a moment. You can see my second slide, right?
Yes.
Okay, because I think there is some. Yeah. So today I'm going to present three case studies. The first two are brownfield projects. One is a fertilizer plant in northern India, and second is a port infrastructure in eastern coast of India. And the third one is a greenfield project, which is a process gas plant. So before I jump onto the case studies, I would like to set the context for today's webinar. And as we know, like India's population is estimated to grow to about 1.7 billion by 2050. And definitely it will lead to huge infrastructure need. So infrastructure is a combination of fundamental system that supports community, region, or country. And when I say infrastructure, it covers from road, railway, ports, drainage system, sewer system. And at present level, these infrastructures are grossly inadequate. Just give me one moment. I am not able to remove this. Yeah. So to support this infrastructure need, engineers are challenged to provide such infrastructures economically and in time. And the solutions that we provide must be sustainable and efficient. So to build a better infrastructure, we need technical expertise, design and build expertise, and operational excellence. So novel construction materials and engineering tools may help address some of these challenges, but dramatic progress may be possible only by developing entirely new construction approach and effective planning and quality control. While developing infrastructure, one of the key challenge lies is understanding geotechnical challenges, its realistic assessment, and providing the possible best solutions. So when I talk about possible best solutions, I'm sure along with me, many of us will resonate with the words of Hugh Golder. And for that matter, I would like to read his words in this webinar. There are two approaches to a natural problem. They are the approach of the pure scientist and that of the engineer. The pure scientist is interested only in the truth. For the engineer, on the other hand, there are many possible answers to a natural problem, all of which are comprises between the truth and the time. His answer must be sufficient for a given purpose. When I say about given purpose, it means evaluation of existing foundations or design of new structures. For this reason, an engineer must make assumptions. Assumptions which in some cases he knows to be not strictly correct, but which will enable him to arrive at an answer which is sufficiently true for the immediate purpose. Mistakes are not made when an engineer makes his assumption. Mistakes are made when other engineers forget the assumptions which have been made. So with this, hello, sorry, can I continue, right? I believe there was some. Okay. So with this, I would like to start with case study 1. So this was like a leading infrastructure proposed by a fertilizer company under its expansion plan, which was the product packaging unit. And it comprises of 3 major structure, that is conveyor belt area, MCC control room, and the wagon loading platform, as we can see on the right hand side of the figure. And the key geotechnical. Sorry, I don't know, somebody's trying to talk to me or?
ભૂલી જાઓ વેકેશનમાં આ પૂછો વેકેશનમાં આવશે જ છોકરાઓ હા ચાલો તો કમ્પલસરી કરી દઈશું
We can unmute him.
ઇન્વિટેશન માટે નથી આવતા
Organizers, please unmute him.
Yeah, but
એક વાર એ वो भी नहीं आते एक बार एग्जाम देने नहीं आए अभी वाले
I'm not having that access. I don't know if somebody can help me.
That's why I said organizers should mute him and we can post this video also.
Oh, okay.
Please continue.
Yeah. So you are still able to view my screen, right?
Yes.
Okay.
Yes.
So basically for this site, key geotechnical challenges in the project were like weak subsoil condition, space restriction due to existing railway track, because wagon loading platform was supposed to be part of expansion. The location was in a high seismic zone, that is zone 4, as per Indian code. And then obviously for any project, it is always a stringent schedule and limited budget. So let us first assess a few conditions which will tell that how the challenges were and how it will be mitigated. So as we see, the investigation was done through boreholes and CPTs across the plot, and it was observed that the top 12 meters was found to be like loose or weak soil, I would say, and there were chances of liquefaction. So even the strange thing is like in the top 2 to 3 meters we found like fines greater than 60%, which may not be that much susceptibility in terms of liquefaction, but 3 to 12 meters was like a poorly graded saturated
19 की
fine
बात
sand,
लास्ट मतलब 20
where the
21 की
fines
बात
less than 10%
हाँ that is the thing.
indicated possibility of liquefaction. Water table was in the range of 3 meters from the ground, and similar observation was also seen from the friction ratio that was estimated from the CPT test. Further, relative density in the range of 15 to 35%, and some lab test also confirmed the grain size analysis for this site. So once this was known, another constraint was like existing railway track. So this railway, I mean, the railway is
Yes,
under the
right.
central government, and we don't have access to execute any work unless we get the approvals. And the approvals was taking time for the client. No, it was delaying the schedule and project because of that approval matter. So client was interested to know what are the ways that we can use the available land and try to mitigate and try to proceed our construction and design. So this was one of the challenge. And then based on the soil data that we had, we initiated liquefaction analysis. As we all know, like liquefaction phenomenon is a state where soil loses most of the shear strength under seismic forces due to sudden rise in pore water pressure. And this is more prominently observed in loose saturated cohesionless soils, which was the case in our site. And there are two variables required to evaluate liquefaction resistance. So a cyclic stress ratio CSR and cyclic resistance ratio CRR. So SPTs and CPTs results were used to assess the condition, and it was found that top you can see my cursor as well, right? So you can see the top 12 meters was below this red line, which was the requirement to avoid any liquefaction at the site. So after a lot of thought process and option, it was finally decided that ground improvement is inevitable and vibrocompaction technique can be used. But before arriving to vibrocompaction technique, other options like stone column or driven piling was not considered. And the reason of stone column not suitable was the availability of the stone material. Like normally we need angular and volcanic rock kind of a stone to get the proper resistance or increase the mass density of the ground. And that was available like from a very far distance. So the logistic cost, and that was like almost coming close to the pile foundation. And for pile also, the cost was coming out to be exorbitant, and the structures were not that heavily loaded. But because of having a liquefying ground, they were bound to go at a deeper depths, and that was creating a stress on the budget for the project. So they were looking for a solution where we can try to eliminate this and make it within the budget and even the time constraint, what they had for the project. So obviously the technical compliance was supposed to be studied for vibrocompaction technique. And as we saw, from 3 meters to 12 meters, the fines were less than 10%. So it indicated fine sand kind of material, which is easily possible for vibrocompaction technique. And then material availability, as we discussed. So it was decided to do some trial works to ensure that whatever we want in terms of capacities that we will be able to achieve. And for wagon loading platform, though it is loading and unloading, but the minimum bearing capacity that was expected was around 100 to 120 kPa, whereas for MCC control room and conveyor belt, it was around 150 kPa. And obviously the time and cost has to be studied along with the possible options. So trial works was supposed to give us some indication on the time and cost that would be needed to cover this whole area. So during the trial works, it was observed that the contamination of top clay silty soil, when we are doing vibrocompaction from say 12 meters onwards and coming back to the top, it was observed that the top 2 meters were now getting contaminated with fine silty soil up to 3 meters. And that was creating a problem in terms of achieving 150 kPa bearing pressure for MCC room or conveyor belt area. So I think in the first time in India, we use this technique. Here, Keller was also our partner in assessing this possibility. And with the help of them, we propose this option to client by using vibrocompaction first and then installing stone columns in that, short stone columns, to cater the need of heavy structures like MCC and conveyor area. And based on that, we did some trial works we excavated and tried to understand like the stone column formation. As you can see in the bottom picture that after excavation, you can see the formation of the stone column, and try to achieve this capacity that is required for the project. Here you can see the wagon loading platform arrangement where vibro compaction points are marked. Now you can see here strange thing that one of the foundation is not covered under vibro compaction because of the railway track which was passing over here. So there was a limitation from client that we cannot go certain distance from the railway track as it comes under the purview of central government, and we were limited to reach only up to certain distance like around 1 meter or 2 meters from the rail track. So one of the we were definitely concerned of this foundation, which will be like on not on improved ground. But then the design was done in such a way that most of the loads will be taken care by this large foundation, which will be on the ground. Loading platform will be covered on this, and only this particular column, which will have a relatively less loads, will be part of this foundation. I hope other audience are not getting disturbed, right? I mean, I'm okay, but Nazim,
can you not mute him? Can you not mute him at least?
Nazim, can you help me?
We can meet him now. Organizers can mute him, definitely. Even we can set the video also.
10th August.
Because I have seen number of presentation, he's there, all this possibility and problems are there when he's there. He's not.
Just a moment, I'll just mute myself.
There is no.
Okay,
I think it
so
is muted. Yeah.
So I'll start again. Yeah. So, okay, yeah. So what I was trying to say is that this particular foundation we were not able to improve, and there were reasons for that, and we have to manage that by whatever the options we had in our hand. And going forward, this loop was getting merged with the main railway line. So there particularly we didn't had much problem, and we could go much closer to the rail track. So that is how the plan were made, and we were ensured. So this also created a need to understand that whenever we are doing any vibro compaction at say this particular point, to what extent the effect will go radially, so that we can understand that what could be the level of improvement. So that study was also like initiated. I am really sorry, Nazim, but maybe I'm also not able to concentrate. Let me.
Also, it is difficult for us also to means listen properly. So
Can I make a call to him? Maybe I know him. Just a moment.
Any other item with permission to chair? Huh?
Mr. Thakur, you are in the presentation and you are disturbing the presenter. Can you please mute your phone, the microphone? Tejas, you
And
can
video
continue.
also. And video
Yes,
also.
please.
Video also.
Please respect others and shut down your microphone right now, and so the presenter can continue. Thank you.
Okay, so I'll just go back. Thank you, RT, and thank you, sir. I hope you can still see my wagon platform drawing, right? Or I need to reshare.
No, yes. Yes, we
It
can
is
see
okay.
it.
Perfect.
Mm.
So, okay, so this was the challenge, and we tried to, so here the need came that no, we need to also understand that how much radially the impact would go for a vibration that would be created at this particular point. And because that will also help us to understand that how much we can improve and what will be the reliability of the foundation that we'll be putting between the two tracks in terms of bearing capacity. So that study was also taken. So after completing all this exercise of ground improvement and stone columns and all that things, we did post ground improvement testing and compared with the pre and post on the same location so that we can understand the difference between the old and the new data. And also the liquefaction analysis was done to understand that how it varies. So as you can see on these charts, we could achieve like more than 60% of relative density. And even the CSR and CRR chart, if we see, like we are more than CSR requirements, and that helped us to understand that we are mitigating the liquefaction scenario during the earthquakes. So, and as I said, like no radial extent. So as you can see in this chart, the 30 to 35% was expected. I mean, was the original relative density of the site. And after improvements from that particular point, if we see, then on an average, it goes up to like maybe 4 to 4.5 meters. 60% or I mean more than 50% of improvement you can expect, but beyond that it roughly goes back to the original thing. So that's the distance you can cover from a particular vibro compaction point. So that distance was also helping us to at least put technically correct that okay, the foundations which will be placed between the tracks will not be having that major issue. Plus there was another argument that trains will be, trains are already moving this particular tracks since long, and obviously the ground would have seen the vibrations to a certain extent in the depths, and that would also support overall performance of the structure during its design life. And with this, as we saw, like we conducted some other tests like plate load test and zone load test for stone column area, and just to ensure that the capacities that we are designing or we wanted are within the settlements. And as we can see from wagon loading platform 120 kPa, we hardly had any like 3 mm settlement. And similarly for 150 kPa of MCC room, we had almost like 1.4 or maybe say 2 mm max, which was much within the settlement limits of a structure. So the outcome of this was like, we use vibro compaction, and maybe first time in India, we used combination of vibro compaction and stone column, which was suiting to the ground need and the project requirements. It was successfully completed, and 5,500 square meter of area was treated in just 1 month using one rig, showing speed of the method, which also helped project to cut down the cost and schedule significantly. Locally available sand was used as a backfill material because this was surrounded by alluvial, alluvial kind of terrain, and therefore the stone which was available was like rounded in shape, which was not suitable for the stone columns, and that was one of the reason, apart from logistic, to not go for stone columns for this development. And the results from SPTs and CPTs obviously showed better relative density. And yes, this method can definitely be extended for their other plant expansion, because this was like initial small structures they were thinking to ease out operations, but yes, they had a lot more land to develop for their upcoming projects. So this definitely helped them to understand the mitigation way for their future projects as well. So now coming to the case study 2, this is the project site is on eastern coast of India, and the site was very vast, but I'm focusing on right now two particular area, that is coal stackyard and stacker reclaimer. And this is mainly to handle the import and export of the coal from the port infrastructure. So the key geotechnical challenges, as common, is like ground is very weak. Here there in the first project it was sand, but here it was like clay, a very soft clay. And again here the site has to be raised by 3 meters. Now raising the site, normally we try to get the good engineering fill material, right? But here we had this problem as well to get the good source engineering material. So we use the dredged material, which was anyway to be dredged for the port infrastructure. So dredged clay was filled on this. Now, when we are filling with dredged clay, obviously the high compression and high compressibility will be in as one of the drawback for this particular aspect. So that has to be considered. Ground improvement was inevitable. And here also the time was constrained, so we cannot go with a surcharge method or no conventional, because it will take about 10 to 12 months minimum to achieve the desired results. So we had to go for vacuum consolidation, but it has its own drawbacks as well, which I'll not take it up in the next slides. And then we also have to de-risk the monsoon impact on the project completion, because project was getting, I mean, if it gets delayed of operation into operation, then obviously there are other project consequences also, and obviously stringent schedule and limited budget. First, we'll go through some of the basic information. So as we can see on the screen, like we had a virgin soil profile that is below dredge field, I would say. So almost 18 meters of very soft to soft clay was there, which had SPTN value in the range of less than 5. Then it was followed by a form to stiff clay, very stiff, hard, and maybe very dense, and was in the range of like -48. So almost 55 meters from the original ground level. Some of the design criteria we decided to analyze, because here the study was required to do some finite element analysis, because we wanted to understand like what could be the possible foundation system that could be placed, so that we can address these challenges, which we'll take it up with consolidation and other aspects. So like 50 years was the design life. Coal stake that was expected to be like go up to maximum height of 14 meter. And here I want to like emphasize, because this will not be the constant height, but coal stake will depend on like import and export, and it will be a dynamic load. But that frequency was difficult to gauge by anybody, like on which point of time and how much point of time particular height will be retained. So it is very dynamic. So in a worst case scenario, we consider like to no, for analysis purpose, at least to understand where we are, we thought of to go for a maximum height of 14 meter as a load, and then see the impact on the ground. And yes, the density of coal 8.5 was slightly on the higher side. We had to take into account of the moist condition as well, because this, I mean, coals are normally, stacking are normally had wet sprays, because they otherwise catch fires. And again, it was on eastern coast, which are prone to cyclones. So it was expected like most of the year, it might be in the moist condition. So that was leading to the design load of like 119 kPa. And yes, residual settlement. Yes, we had to tell the project that no, we cannot expect like 25-50 mm for coal stack at least, and it has to go like 200 mm or maybe more. But that could be like no set criteria for us to start with. And yes, 80 kPa would be the reason, because of the vacuum consolidation, which I'll not take it up in the next slides. So vacuum consolidation was also first time in India. For this project, we used it as a method against the conventional ground improvement technique. And here there were two options. This all itself calls for a new session, because it's a vast subject altogether. But I'll just touch upon some base to get understanding on this particular aspect. And here we used two different techniques. One was membrane type and another was tubing type. But for this particular location where I'm talking about is about membrane type. So membrane type, no, when we talk about vacuum consolidation, I talked about drawback. And when I said drawback, it was like we cannot go beyond 80 or 90 kPa, because 100 kPa is the atmospheric pressure. And when I'm trying to create a vacuum, I cannot go beyond that 100 kPa. So in that case, this was a limitation for us, even though our expected load was right in the range of 120 kPa, but we cannot go beyond this. So we had to put some additional surcharge, and again, surcharge is a cost. So we use the water column, which is easily available in the sea beside the site. So embankment was made on the ground, and then it was filled by 1.2 meter of height to create additional pressure. But still, it took us to like say 90 or 92 kPa at the max. But that was the attempt made to increase the consolidation. And there are some parameters that were used for installation of PVBDs and the levels of the PVBDs. This pressure was applied for 90 days. So here also trial works were done to understand that to achieve this particular SPC or requirements, how much time we need against like 10-12 months in the conventional. So 90 days was coming out to be an average good time to get this particular capacity. And the PVBDs were installed up to like almost 12 meters below ground. So proposed ground improvement, again, like has a residual settlement, definitely if the load increases from 80 to 120 kPa. So that was acknowledged during this study. So then we went into FEA analysis, and it was important to understand the geometry and ground model that we put into it, because in any software, the input defines your output. So if it is not right input, then probably your output may be misleading or may not give you the exact picture. So in that case, we all were aware, like, no, we are trying to correct the worst case scenario, which may not be the case in reality because of the dynamic loading, but still we have to do something. So as you can see over here, like two coal stacks on the side of stacker reclaimer. Eventually, our intention was to eliminate pile altogether, but a stacker reclaimer is a critical equipment, and we cannot, just overlook that. And for that, we need to use the pile foundation. So pile foundation was inevitable for stacker reclaimers at this location. So this is a location where stacker reclaimer was placed, and then PVBDs were placed below coal stack. There is a road on one side for maintenance and other access perspective, and some dimensions over here to understand, like, what is the intensity of the particular loadings. This was the ground model. Like dredge mud was also taken into consideration because this has to be done after filling to +6 elevation. So 3 meters of dredge mud was placed. Then soft clay layers were divided in based on the parameters arrived from the different testing, and then very stiff clay and hard clay for the model purpose. The piles were up to like -40 meters. I mean 40 meters in total length. So -35 or so. It went up to that. So in terms of geotechnical data interpretation, yes, we had to look around because it was an brownfield project. So we had some information from the existing infrastructures and facilities. So we used that, as well as we conducted new investigation for this particular area. All was combined and some analysis were done to arrive at, like would say 95 percentile kind of probability for these parameters, and still being a bit conservative because we are dealing with clay, and that too like very soft. So we do need to understand the severity of its impact. And these are some charts that were developed. And then obviously the parameters calls for shear strength, coefficient of consolidation, and compression ratio to understand the settlement impact. And then we had to prepare a table to understand the soil model and design parameters that will go into the software to get further analysis. So important was the construction sequence that we are going to use, and that we were trying to simulate so that we can get close to more realistic, because I cannot say in soil that 100% this will be the answer, but yes, we can at least come close to the realistic picture or try to gauge the range where we are looking at. And as you can see, there are different construction sequence that were developed, starting from like initial ground condition, and then filling dredge, allowing for like 30 days, and then constructing pile foundation, living after pile construct. I mean, after applying pile foundation, 7 days were like allowed for consolidation analysis. Similarly, construction of prefabricated vertical drains, and then again applying vacuum pressure, maintaining vacuum pressure for 90 days, removal of that, high strength, placing of high strength geotextiles, applying against stacker reclaimer load of the equipment on the piles, and then different stages. Like first stage will be for 10 meters height, and then the next stage will be for 14 meters height, which was the maximum height we were expecting in its design life. And then consolidation analysis for 50 years. Additionally, we also tried to like check up to 75 years in terms of 1.5 times of existing design life, though no requirement was up to 50 years, but as a part of analysis, we just took one step more to understand its impact. As an outcome, yes, vertical settlement, you can see on the top, the yellow line shows the construction sequence when it was applied, and how, because of that sequence, how the settlement or the ground was behaving. So on an average, you can see like 6 or 7 points were selected, as you can see in the bottom, like A, B, C. So like center of coal stack, edge of the coal stack, and then pile foundations on top of it, and then again on the other side of the coal stack. So you can see post-construction. So I say post-construction means after all the consolidation has happened, which was expected from the PVBD and no other vacuum pressure. And then after finally putting the coal stack up to like 20.6 meter, that is 14-meter height, that was our end of construction. And then from there on, if I wait for 50 years as it is, then it was showing me around 345 mm of settlement, right, at the toe of the coal stack. And if I talk about the center, it was coming around 320 mm. Now it is a bit strange to see like center we are getting less, and on the coal stack we are on the edge we are getting slightly higher. The reason being like because no the PVBD were restricted to this particular toe and no further PVBD were installed because it was coming very close to pile, and we also didn't want throughout the life of pile this PVBD movement will impact the, I mean, it will make it more complex in terms of loading on the piles. So that is what the difference is. And here it was like more covered through PVBDs, and consolidation would have already covered because of the vacuum pressure. So relatively you're finding. But even if we increase 1 or 2 row beyond this, our no assessment said like we could go maybe somewhat less than 320, but that anyway was not making much difference to us. So our design requirement was 200 mm. We were definitely exceeding that. Again, the reason was like against 80 kPa, we are also applying 120 kPa, and that was the worst case scenario. So we have to acknowledge that. But this was the finding from this particular analysis. So this also gave us vertical settlement on the piles. Like we had two lines of piles placed, pile 1 and pile 2. So for each particular construction sequence, we had assessed like what could be the vertical settlements and lateral deflection on pile top, and what is the maximum lateral deflection and corresponding RL for that particular value. So this is the chart of it, and as you can see, like maximum for 50 years design life, so it is 37 mm, and if I talk about maximum load when it is applied, it is 34. So like 3 mm was the long-term settlement of the pile. However, from the start of it is like almost 34 mm, which was like significantly high. Same is the case for lateral. So finally, we need to understand like what could be the load on the pile, so that we need to ensure that geotechnical capacities are met. And as we can see, the net axial force is in the range of 3000 kilonewton. We always have to take the worst case. So pile 1 was more compared to pile 2, and pile 2, the reason being like it was having some road and the PVBD was higher, plus the dimension on both the coal stack was slightly different. So this difference could be seen in pile 1 and pile 2. However, no, the shear force, bending moment, and axial force were considered for the maximum one, and we have to address this in our geotechnical capacity. These are some outputs just to showcase like how the things have been estimated. So we can definitely get deform mesh at different construction sequence that we want. So like at applied vacuum pressure, you can see like the line going down and trying to create the settlement within the area that has been defined for the design. Similarly, at end of 50 years, you can see some settlement of in the center portion very easily. And these are the analysis in terms of lateral deflection, axial force. The charts, I think all the engineers would be well aware of, and SF diagram and BIN diagram to understand like what could be the maximum values and at what elevation. I guess obviously this is a very soft clay. Negative skin friction would be in play, and we have to acknowledge that. So this also helped us to understand what is the neutral plane, or I would say like the change of from negative to positive skin friction, and what is the magnitude of that. So that also helped us to understand that at what elevation we need to ensure that bending moments are being taken care by the reinforcement that we'll be providing in the piles. And apart from that, we also have to see the stability analysis, because we are still resting on the soft clay, though we are improving it, but not to the extent it has its capacity to get improved. So in that case, it was observed that most of the failures were within the coal stack region. Nothing was passing through the foundation, and even in the coal stack, it was like maximum, with a maximum height, it was coming around 1.9, so which was much above like 1.5 we normally took as a standard guideline. So at the end, like analysis showed us a few things, like we were definitely exceeding the geotechnical capacities. However, in reality, the loading from the stucker reclaimer and coal stack will be much lower than the loading cases adopted for this analysis, as the coal stack loads are dynamic and will not be like up to the maximum height for full 50 years. So the structural forces and bending moment on piles are expected to be lower than the values obtained from the analysis. So obviously it was not meeting, but still we had to address some portion of it. So pile length and diameter were increased and meet the capacity requirement. Additionally, the piles were connected with tie beams and pile cap, because here we are trying to now expedite the schedule by not doing any ground improvement between the piles or not close to the piles. So initially plan was like to first do the ground improvement and then go and install the piles, but that was creating a problem with the monsoon coming and other project schedules. So this analysis is also helping us to understand that what could be done in pile so that we can avoid that and we can gain some time. Reinforcement in piles were supposed to be increased to resist bending moments from both, like from the horizontal load as well as from the drag load that would be coming on the piles. And then working platform, obviously it will be unimproved. So for piling case, we have to make sure that some base working platform is created so that it could be drilled at site. And then pile load tests were evident. No, it told us the performance of the design values that we used, and it was meeting our post construction requirements. But this was done all after construction of pile and completion of ground improvement. But this was proposed that this would have to be done to ensure that we are not blindly closing the case. And then this analysis helped us to de-risk the monsoon for sure effects and provide any safe design for the foundation. By constructing piles prior to GI helped definitely us in project schedule, but then the GI cost and schedule saving within the Stucker reclaimer was compensated by increasing in cost of pile foundation leading the safe design. So I would not say like cost point of view, but yes, time point of view definitely helped us, and the time is money, so indirectly it helped us in overall costing, I would say that way. So coming to third project, so like I'm trying to come back to my main point, which I was trying to say, like, as an engineer, you always have to play between truth and the real time frame and try to make some analysis. And obviously the soil being a very complex material, engineering judgment and your experience and exposures helps us. And for that, you cannot simply rely on your this thing, but you have to assess it in all the way around so that you are making an informed decision rather than like, just haywire decision like that. Coming to case study 3, this is a mega greenfield project located in Middle East region, and it comprises like it's a vast site, but I will just focus on 2 ammonia storage tank that we used for that we are going to construct on this particular site. Each tank has a storage capacity of 70,000 metric tons. So you can imagine the size of the tank. It's about close to 70-80 meters in diameter. Site was highly undulated, and like in the initial levels were ranging from plus 2 meter RL to like minus 20 or 22 meter RL. So it was a huge cut and fill to optimize the earthworks. And obviously when you fill it, if you go layer by layer, the time, if you can see, the site is like about 1 kilometer by 2 kilometer kind of spread, and layer by layer compaction will definitely call for a lot of time and efforts. So here dynamic compaction was a approach taken in terms of the area and the elevation that we used to use, we need to get from the as output. So again, challenges were like stringent performance required because it is an ammonia tank. We cannot allow higher settlement. So 25 mm was the restricted settlement, and differential settlement should be less than 10 mm. Design life for 50 years. Foundation has to be rested on a backfill soil. Backfill height was around 4 meters from the natural ground. Free fall was observed during borehole drillings in some of the preliminary investigations. So that was also like a concern towards that why this is happening. 20 to 100% of drilling fluid loss was encountered in most of the boreholes in the preliminary investigation. And desktop study, like since it is a greenfield project, we didn't had any information in vicinity of such large scale projects. So we didn't had any understanding like what is the ground and how it is. So a lot of desktop study has to be made, and it was indicating us that site may be prone to cavities below ground. So it was very important for us to for lightly loaded structures, we might not be that much of a worry because the loading intensity is less, the spread is more. But here, being a tank, and that to ammonia tank, it has to be like pretty sure that what we are dealing with, we should know that. And that was the reason why we had to go for like extensive investigation. So geophysical survey was proposed using MSW, like up to 25 meters 25 meters depth for initial scanning, I would say. Then sinking of boreholes like 70 meters deep, almost equivalent to the diameter of tank, just to ensure that there are no loose pockets even below the tank at such a depth. And crosshole tomography was conducted between the boreholes or across the tank to understand if there are any cavities within the boreholes. So like I think 7 boreholes in each tank. So 14 boreholes were drilled total. And site-specific seismic hazard analysis was performed. though site lies in a, like I would say, low to moderate seismic zone, but yeah, it was important because now we are putting up a structure or infrastructure which is very critical in terms of hazard. So geophysical survey using MSW was conducted. MSW is multi-channel analysis surface wave. And the initial objective was to image the subsurface to a depth of 20-25 meters below ground, mainly to analyze the stiffness of the ground, I would say in terms of consistency of the soil, or else detect any anomaly in subsurface conditions or any associated cavities or weak zones at the proposed site. Uh, the data was collected by using 24 channels. I just tried to put a schematic understanding like how it works. So geophones are being used at certain spacing, and the lines are being drawn, and the line intervals were like at every 5 meters. So as you can see over here, like these are the blue lines which were along which this survey was done. And then these were mapped in terms of the data. So in on all, like 10,770 linear meters was covered for the complete site. And as you can see, like data processing takes an efforts. So because you get in terms of waves and velocities, but you need to filter the noise. So it is also a specialized study. And the right people were put on job to get these reports. And finally, after doing all this analysis, they provide us this kind of section, which tells us kind of a scanning, I would say, which tells us like what is the range of variation in the shear velocity. These are some slides to showcase like how it helps. So as you can see on the first right-hand side, 2D mapping plus the boreholes which were already drilled were placed on that, superimposed on that. Though boreholes were done up to 70 meters, but top 25 meters was superimposed, and try to understand that whatever the soil is collected in terms of samples, whether they are matching the results from the MSW. And as you can see, like most of them are in line, but there are certain areas where which were not covered with boreholes, right? So that particular area, if the shear velocity was like less than 200 meter per second, kilometer per second, some indication was given to us that this should be further explored and ensure that this is only just I would say weak soil rather than any cavity or any openings. So that kind of points were identified on the plot plan, and re-investigation was done for that particular instances across the plot. Apart from that, depth slides were given, wherein you can see at a different elevation, if the ground is cut, then how it looks in terms of wave. So you can see like at a lower elevation or at a shallow depth, I would say 5 meter, it's more of a low shear velocity zone. But as you go on increasing the depth, the density or consistency increases, and you can see more towards green and yellow and red. So that indicates no that soil is better at deeper depths. However, you can see the two tanks over here, and these are the location of two tanks, the boreholes of the two tanks, and you can see the distance between them would be like hardly 40 meters or maybe 60 meters at the max. But you can see the variation between them in terms of shear velocity. So the ground, though we do believe like no, we sometimes we get a, uh, I mean sometimes we get, as a geotechnical engineer, people say that if you have 2-3 boreholes, what difference does it make? You can still analyze. Yes, we can do that for sure. But then we also have to understand like to what structure you are dealing with and what could be the variation, and if that variation is really impacting or not. So this is just to showcase like there could be still a difference in terms of stiffness, even though they are very close by. And especially when you are dealing with the weathered or sedimentary kind of material. Because the formation takes in thousands years, and definitely it has its own challenges. So yes, boreholes were drilled, and this was the section profile. And as you can see, the top layers are like more of a sand or sandy strata, and then followed by weathered rock. Again, there were certain locations or layers, I would say, like still not formed into rock, and were still into the soil state. And then some interpretations. So on the left hand side, if you go, it will find the SPT values, and on the right hand side, it indicates the RQD values. As I said, like rock was more of a, I mean, these are these are detailed classification, but in broadly, I couldn't say it's more of a sedimentary rock. So design parameters were no, again analyzed based on lab testing, field testing, SPTN values, and try to understand that what could be the design profile if we need to estimate the capacities. This was the cross-cell tomography. So between, as I said, like now the center borehole was used as a source, and all the peripheral boreholes were used as a receivers for geophones, and the waves were passed on from each boreholes and also from borehole to borehole to map in all the direction the shear velocity. Again, like compression velocity as well. And as you can see here, this particular range, right? This shows the P waves, and P waves are more than almost like 2.2 or 2 onwards. You can see generally if P wave is less than 1.5 or 1.2, there could be a possibility because now water density is like, I mean, if you conduct P wave in water, it gives you around 1.5. So if it is less than, then there could be a possibility of like a cavity or so. But here we could see like all the, I mean, all the sections that we drilled, that we performed were having more than that. So that and assured us that no, there is no such cavities, at least that we were not thinking to be in this particular site. So that helped us to understand more in detail. Here you can see on the left hand side the shear wave mapping. So where there are rock layers, you can see like bit better shear velocity. But when there are certain layers which are still into formation, the shear wave velocity drops, and you can see two different clouds forming on the top as well as in the later part of the boreholes. Same is for another tank. As I said, like two tanks, two different stiffnesses. So you can see the same over here as well. The top clouds are like more of a green rather than blue, indicating like better stiffness. And this we actually no felt during construction as well. Like when we were doing the piling for this particular tanks, we could see the difference in pile construction in both of this tank. Like this tank, which I am seeing like green and blue, I mean green and yellow, had much pretty and without any no construction issue. But where we had this blue, we had some construction issue in terms of reinforcement getting pulled out and over concreting getting into the ground and all. So finally, from the second phase of investigation, we got this capacity chart. And strangely, you can see the capacity chart normally we see like goes on increasing. But here, since the formation was like changing from soil to rock to soil and again to rock kind of thing, it was like having bit tricky graph. And for us, like this could be the level and to meet our design requirements. But still, like this was I mean, in this particular region, and especially when we are having board cast in situ piles, we need to ensure that the tip is clean, and we should not fully rely on end bearing component. And because of that, it was also like no sense of understanding that we should try to avoid end bearing component. So if I avoid end bearing component, then my capacity drastically drops because my skin friction component was very low for a given length, and that was asking me to go for a deeper depth, which was again like not right in terms of cost and schedule. So then we thought to go for instrumental pile testing further down one step. And then we conducted initial pile load test on the site. Strain gauges were installed at different elevation to understand like what could be the resistance that we can get from skin friction. And even the lateral load test was also performed. So total 4 pile load tests were conducted on the site. One was specifically for the tank and other for in the nearby region. And for all of them, strain gauges were installed at different elevation to understand the skin friction generated by the each layers. So on and all, after completing all the test, this is what the summary we got. So like say for 1000 diameter and 17-meter pile length, if I use my preliminary investigation, it was indicating me around 3500 kilonewton. I mean, FOS2 I have considered because if I'm going for a pile testing, I can reduce my reliability. I mean, I can increase my reliability and reduce my factor of safety. So generally we take 2.5 to 3, but since I was comparing this, so I'm using factor of safety 2 for all the cases. So as we can see, like 3500 was expected value from preliminary investigation. From basic engineering investigation, it went to 5500 as I was showing that chart. But here it was like combination of end bearing as well as skin friction. But if I use the test pile results, and if I only consider the skin friction generated on each strain gauges, and that was leading me to around almost 4050, which was meeting my requirement of 2800 or 3000 kilonewton requirement for my capacity. So that way it was helping me without relying on end bearing component, I would say. And further, like no initial test was conducted to understand the design, but then after design also, like 1% of total working piles were proposed to be tested on the site to confirm the design pile capacities. And as you can see on the right side, these are the piles that has been casted for this particular tanks. The project cost and schedule was significantly improved due to enhanced pile capacities that we adopted based on instrumented pile load test, and helped to reduce almost 50% of its original proposal. And then initial pile load test also helped us to foresee pile constructability issues that we would have maybe impacted our schedule and variation from the to the client during main piling works when the contractor is on board. So this also helps to avoid this kind of variations in the project. And obviously more confidence on the ground condition was established based on the outcome from various tests performed, starting from preliminary investigation to MSW to cross tomography and even the instrumented pile load test. And no, specifically for the tank foundation, it was a huge benefit to the overall project in terms of cost and schedule. So with this, I would like to end, but yes, for sure, I would like to give my gratitude to all the team members who were part of this project. Along with me, a lot of hard work has been put into this, and always, it has been motivating to work on challenging projects. And as I say, learning through exploration is always a key to success. So the more you explore, the more you learn, and it's a cycle. So more you learn, then more probable solutions you can provide not to mitigate the challenges. Thank you. I hope all are awake, right?
Yeah. Thank you, Tejas, for a very
Yeah.
good presentation. You have taken 3 slide studies, case studies. One is particular plant, which was in zone 4 in challenging soils, going up to 12-meter weak soils. And then water level was about 3 meters. Another constraint was railway approach, which was dealing the problem. So you adopted this vibro compaction technique. Was utilized with trial works with stone column, mostly first time in India. That's what you are claiming. But then in your initial stage, you say that stone columns you discarded because there is no good stone available, which is required for the stone columns. And then why again you went for stone columns?
Yeah, so here the thing was like we were not able to achieve with vibro compaction the desired capacity. So we had. Hello.
Can you hear me?
Yes, I can hear you. I hope.
So my question is that when you're saying initially that stone columns are abandoned or then again you went for the stone columns only. Of course, those are short stone columns, so
Right.
volume required will be less. That was the reason. But initially you're saying that the stones are not available, and then you're saying that you can put the stone
yeah,
columns.
so I understand your point. So like stone columns were not available. Maybe what I was trying to say is that it was available at a very larger distance or far distance, I would say, like more than 200 kilometers. So bringing them from that far was adding a logistic cost to the project. And if I would have gone with stone columns for the whole area, then the number of that volume would be like very high. So to avoid that, we selected vibro compaction. But for the instances like MCC control room or the conveyor belt area where the requirement of bearing capacity was high, we used short stone column. So that reduced the volume that has to be brought from outside, and therefore it helped us in managing both low volume as well as meeting the design requirements.
Okay, thank you. The second was your cold stack yard and
Yeah.
stacker reclaimer.
Correct.
Here you use this ground improvement by vacuum consolidation.
Right.
First time in India. It was 18 meters soft clay and all those things you are in. And then
Yeah.
membrane type and tubular type both were used.
Correct.
Correct?
Yes, yes.
And the detailed construction schedule was adopted and was observed very strictly, which helps
Right.
you to mitigate all the problems which were enforced. And then third was your ammonia storage tanks. It was in Middle East area. It was a huge tank of 70,000 tons, only about 70 meters dia. And it was here you conducted this MSW, then all these days, before compaction or both before compaction and after compaction also?
Before compaction, we conducted MSW. The intention was to understand cavities or any anomalies in the shallow depths, which was like confirm that we don't have such a major issue on that. Then after compaction, we conducted this cross-hole tomography just to ensure that up to the depth of 70 meters, we don't see any loose pocket or any cavities over there.
Okay. Thank you. Thank you very
Thank
much
you.
for your good presentation. Thank you.
Thank you.
Over to the organizers.
Sir, do you have the photographs for vacuum consolidation?
Yes, we do have.
Then actually, it's a being new technique. It should
Right.
have shown it would be. And
I
sir,
think one of my colleague who was part of this project, he conducted a full session on vacuum consolidation for this particular project. I don't know if he is part of this session as well, but that was already covered in IGS, maybe 2 years back or so. I don't know. We can check, but yes, we can definitely provide you like if you are interested in specific to this. So I just tried to touch upon that particular aspect, considering this particular case study. A full
In
session on
third-
this, like both the
in-
methods were covered in IGS. Yeah.
in third case,
Yeah.
when the secondary investigation was carried out, was it limited to 25 meter or full length?
No, it was for full length, 70 meters deep investigation.
What is the sense?
What is the sense in the sense? Like how much, why you need to go that deep?
Because for the 25 meters top depth, you were analyzing and some difference was there. And that is why you carried out the secondary investigation.
Right.
Then when you don't have to think to compare these things, then what is the sense of investigation up to 70 meters?
No, I see. MSW has some limitations because you cannot, you will be transmitting the waves from the surface and you cannot go beyond certain depths because it might create a lot of noise and it might be difficult to interpret. So that limitation was like 25 meters. So initially it was a greenfield project. So first we wanted to scan the top 25. We found that in top 25, this was, I'm talking right now only for tanks, but this was done for across the site. And some of the locations, they have identified that there is a low shear velocity. So you need to explore further and say that, okay, whether it is because of the loose consistency of soil or if there is any pocket over there. So for the tank location, when we went for detailed design, so for that, we had to particularly go for tank specific investigation. And there we proposed like 7 boreholes for each tank. And for tank of such a huge diameter, though the pressure bulk.
That is justifiable because it's a preliminary or main investigation. What I am talking is about the additional test, additional investigation.
PMSW was the first step that we took. Second was the tomography. It was not other way around.
And then after you carried out once again investigation, additional boreholes. So that what I mean is that should be limited to 25 because you want to compare or you want to check the 25 meter difference only because you found some difference between the things and here in this 25.
Okay, then I think let me correct. Yeah, let me correct again. So see, preliminary investigation was before MSW, where the site was like in its original condition, right? Then in that investigation, we saw some drill bits dropping. We had this fluid loss, and parallelly we were doing desktop study. So that was also revealing that probably there could be some probability of cavities and all. So because of that, we said, okay, let us scan the site because we cannot go doing boreholes at every 5-meter interval. So in that case, we tried to scan the site, and with scanning, we saw that, okay, top 25 meters, we are not seeing any major issues in terms of cavities. So that was rest assured. Now it comes to detailed design investigation. So that was done 70 meters after that. So preliminary was the first, then MSW,
Okay,
and
that's right.
MSW indicated some points. So tank was explored up to 70, and then in tank also we did cross hole because
So
we
that
wanted
was
to,
detailed.
yeah,
Detailed
correct.
investigation was the second.
Yeah,
Okay,
that was
that's
second.
right.
Yeah, okay.
Yeah, thank you very much.
Yeah,
Thanks.
thanks.
Any more questions? I request organizers to take over now. Thank you.
I think there are few questions on the chat.
Yeah, that you can answer. Definitely you can answer that.
Yeah. I think one question is, I would like to ask CMC. Yeah, I would like to ask. Yeah. Okay, so yes, CMC rigid inclusion was also like on table, but then probably the cost was significantly high, and it was also creating like a lot of schedule delay, because we are in CMC. I understand we use cements, right, and that cement cost is significantly high. So against that, and in any case, like when we are filling with dredged mud, like it's, I mean, in Hindi we say dal, right? So it's kind of that kind of material. So we definitely had to go for vacuum consolidation first. And even in that particular area, like most of the structures are on pile, no, which are critical. And others, non-settlement sensitive structures, yes, we can no rely on this thing. Plus, here, let me tell you, like, no, here 18 meters of the original depth was of very soft clay. Plus, we have added 3 more. So it was like taking to 21 meters of that. So I'm not sure CMC, can it be possible up to 21 meters or not? Because that might be, even if it is possible, it might induce a lot of cement cost and other cost and manageability cost. Yeah.
Sir, hi, sir. Komal here. So it's the
Yeah.
same question I've asked in the chat box regarding the
Yeah.
CMC. Actually, I'm facing the similar issue in one of my project at JNPT area. So in that case, Menard is when client is offering for this a design build contract. So Menard have consulted us for that. Even I'm not sure for the CMCs, but they're saying that it can work. And even when the client have compared the cost, then even the cost was less as compared to the vacuum preloading consolidation with this PVDs. So
Okay.
just yeah. So even for CMCs also, it's even new for me. So just wanted to know whether you have some statistics.
We have not used on this particular project as far as I was part of this project. But
Okay.
one thing I can say, like, no, CMC might be useful when you need to no get higher bearing capacity. As I said, like in coal stack, we were not looking for like much requirement in terms of capacity against settlement. So maybe CMC would be more useful when you have to place something with a stringent settlement criteria or no in against a very high bearing capacity requirements. So that could be one of a better option against vacuum consolidation for sure. But yes,
In my
it's
case also,
still,
it was
yeah.
not high loading requirement. It was a warehouse, basically ground structures,
Okay.
where even SBC of 10 to 15 kp, ton per meter squares was also sufficient.
Okay.
Yeah. So
Yeah, sorry, but I don't have a specific experience to CMC. But yes,
okay,
we
sir.
had
Noted.
this initial discussion on table, but then eventually this was working out to be a better option, because here, though I'm talking about coal stack and stacker reclaimer, but this site is like spread across large area. So we
Correct,
also have to
correct.
take that into account, like how we can manage economically.
Noted, sir. Yeah, it was wonderful presentation.
Thank you. You liked it.
Particularly the valuable learnings as far as the detailed geotechnical investigation has been taken up by you for the third case study.
Right.
So that was wonderful. Yeah. Thank you.
Thank you. I think one more question is from Pankaj. How can we ensure good reliability for MSW testing? Yes, MSW compared to, if I say, against cross-hole tomography may not be that high, because with, I mean, anything what you are measuring is from the surface, and it goes a lot into interpretation of the waves, and a specialist is required. It's not an easy thing that we do normally correlations with SPT and CPT. So I would say like reliability also take into account of the people who are selecting for the job. And they should be right people and right this thing. And again, there are a lot of noise has to be filtered out. It's similar to dynamic testing also, right? In dynamic test, we do integrity and we read the waves, but then we also need to understand that whether the waves or the results are misleading or they are providing the right results. And therefore, MSW should also be verified by further exploration, as we did in this particular project by conducting some of the locations where we found low shear velocity. So that way you can verify, but you should not, I would say, like, in my opinion, you should not only rely on MSW and go for design.
Thank you, sir.
Yeah.
Okay, so the entire webinar session was excellent. All the 3 case studies were very well explained. So thank you, Engineer Tejas, for accepting our invitation on behalf of IGS SC3, and we thank you for accepting our invitation to deliver this session. Thank you.
Thank you. Thank you, Nazim.
So we end this session now.
Yeah. Thank you all. Thank you for being a nice and good audience.
Thank you all.
Thank you all.
Yeah, good
Thank
night.
you.
Good night.
Thank you all.